Welcome, guys. Here we have another question based on lesson plan G. So, in continuation to what we have initially, whereby we actually deal with reduction formula of just a single trig, but now we have two products with different powers or the same powers. So, it depends. So, how will you solve this kind of question? So, it's very, very direct. Now, the solution to this simply implies that you will let this time around, you are going to let I of m and n together, the two powers m and n, respectively. So I of mn equals integral of sine of mx cos nx. So remember that this is the first thing we used to do. We make an assumption. So then after making I of mn to be equals to this, then we will decide to reduce the other part, which is cos nx. Then that will be integral of sine of mx. Remember the pattern we used to use, whereby n is greater than or equal to 1, and I will decide to rewrite cos nx in another format. Cos nx can be written as cos of nx, n minus 1 of x, then times cos of x. I believe you agree with this. It's still the same thing. So here I will leave sin mx alone, then I'll go ahead and reduce this cos nx by saying multiply by cos of n minus 1 of x, then times cos of x, finally with dx. So therefore I can go ahead and apply integration by parts. But you have to take note of this. So that means here in this case, all these will represent my u, integral of u dv. So then all these will represent dv. So this in this case now, we actually let u to be equals to sine of mx cos n minus 1 of x, and then we let dv represent cos x dx. And we all believe that by the rule of integration by parts, uv is always equals to u dv. The integral of u dv is always equals to uv minus integral of v du. So this is the definition for integration by parts. So here in this case, I have my u, but I don't have v. To get v, that's very straightforward. Just integrate both sides. You end up having v. I've explained that in the previous video. And then cos x, to integrate is very easy. So I need du, that's the problem. So if I need this du, I will quickly differentiate this u with respect to x such that this is actually a product rule. Yes, this is a product rule. In the case of you need to use product rule formula, then that will be uv minus integral of v du. Then in this case now, forget about this u and dv so that you not get confused. I don't want to use another letter so that it will not be it's not going to be very, very confusing. So now look at this. Let's call this our u, and let's call this our what? Our v. That's product rule. Then by formula, by product rule formula, you always have uv prime plus vu prime. So that's the rule of product rule. Then looking at this, trivially, my u is sine m of x, right? So then my v is cos n minus 1 of x. Now what I need now is I need u prime. To differentiate this one now, that should be m comes down, and then differentiate sine x, that should be cos x. Repeat everything back, then that will be sine of m x, but you need to subtract 1. That's how to differentiate. And then similarly for v prime too. V prime is differentiate this thing. N minus 1 comes down, right? Then differentiate cos x, then that will be minus sine x. Then you still have to repeat everything back. Cos, then you subtract 1 from the power, n minus 2 of x. So this is how it works. So therefore, the du we are actually looking for, the du dx we are looking for simply implies uv prime. This multiply this. And when this multiply this, trivially, we have negative of n minus 1, this times this. Then you notice that if this multiply this, I will end up having sine of m, then with plus 1, m plus 1 of x. Then I have cos of n minus 2 of x, trivially. So that's what you're going to have. And then plus v, which is this, then d. When I multiply this and this together, I'll end up having m cos x times this. Then I think this is m minus 1, 1 cancel 1. Then that will be, I'll be left with just cos n of x with sine of m minus 1 of x. You get that point? So that's how it works. So therefore, we decide to make du the subject of the formula. When you make du the subject of the formula, we end up having um, minus n minus 1 sine of m plus 1 of x cos n minus 2 of x plus m cos nx sine n minus 1 of x, all in dx. So when you multiply both sides by dx. So now I have du, which is what I need in this formula for production for integration by parts. I have my u. I have my u, and I also have v. Okay, I don't have v yet. This is, I can easily get my v from here. From dv equals cos x dx. If I integrate both sides, I will end up having v. If you integrate the v, you have v. That was normal thing. You should have known that. And then integral of cos x, that is sine x. So this is what we have for v. So I have my d and I have my v. So that's sufficient enough to get what I'm looking for. So therefore, recall that your high m of n, which is equals to this integral which I want to solve, integral of u dv, and the formula is given as uv minus integral of v dv. You all agree with that? And now what is u? This is u itself, the main u I have initially. That is sine of mx cos of n minus 1 of x, right? And then v itself is sine x. So I'll multiply this by sine x times sine x minus integral of v, the whole of this, then multiply by du. Sorry, v is this, then multiply by du. So I'm multiplying sine x with this I have here. So I want to do that straight up. So if this first term here multiplies sine x, there is a 1 here, there is a 1 here, that is n plus 2. So I'll end up having negative of n minus 1 sine n plus 2. I hope you agree with that. Then with this cos n minus 2 of x, right? And then if this term here multiply this sine x, I will end up having plus m cos nx sine, minus 1 plus 1, that is just mx. Then all into what? Dx. So all you just need to do for me is to just simplify, break it down. So when I decide to continue, I will end up having, if this multiply this, I have sine of n plus 1 of x cos n minus 1 of x. Then I need to split this up. So if I split this, minus times minus, I will end up having a positive sign. Then the n minus 1 comes outside of the integral. What I have left is sine of m plus 2. Now you see this m plus 2, I can split it up as sine mx, then with another sine square of x. Do you agree with that? So it's still the same thing. Then finally with this okay, then with cos of n minus 2 of x. I think this is okay enough. Yeah, the next thing now is to multiply this minus and this plus, should give us minus integral with this, should give us, okay, I'm bringing the m outside, then I'll have an integral of cos of nx sine of mx, right? Then I have dx. They both have dx. Yeah, dx. So from here, we can still break it down further. Having sine n plus 1 of x cos n minus 1 of x plus n minus 1. Then, if you look at this clearly, this sine square x, I can write it in another form, that is addition formula in trig. Sine square x is equals to cos square x minus 1. Yeah, sine square x plus cos square x equals to 1. Then, no, that would be sine square x equals to 1 minus cos square x. Sorry for that. So, then from here, we should have integral of sine mx. Then this becomes 1 minus cos square x. Then with cos of n minus 2 of x dx. Finally, with this last one that I have here. So the next thing to do from here is you split this up. You open up the brackets. This sine mx and this cos n minus 2 of x is multiplying 1, and at the same time is multiplying minus cos square x. So if you go ahead and simplify that out, or you multiply it, this is what I will get. This is n minus 1. I will end up having integral. This multiplying 1, I will still have sine of mx cos of n minus 2 of x. Do you get that? Now this will multiply this. I'll end up having negative of integral. Take note there's a dx here. Minus this multiply this. I'll end up having sine of mx. If cos square x multiply this one, then 2 cancel minus 2. I'll end up having just cos n x dx. Close the bracket. With the last one I have a m integral of cos nx sine mx dx. So you just have you need to do this just gradually. You don't have to be, you don't have to skip step. You don't have to skip step. Just do it one after the other. You get the concept clearly. So in continuation, I of mn still remain as this expression. So I want to open this. I want to open up this bracket, and I'll end up having sine of n plus 1 of x cos of n minus 1 of x plus, then looking at this, n minus 1. Okay, this is very straightforward. I can easily see an assumption from here. This is sine of mx. Remember that we made an assumption from the beginning that let im comma n represent sine ms cos nx. So if you have n minus 2 here, this will be n minus 2. If you have n plus 1 here, this one will be n plus 1. So now let's come back to this. So the assumption can be easily made here, whereby what I have here, sine mx cos n minus 2 of x, represent I of m comma n minus 2. That's very true. Minus what I have here also represents I of mn, m comma n, right? So it's making sense. The same thing applicable here. When you rearrange this, you have sine ms cos nx, which is the assumption for what we made for what? I of mn. So it's making sense. So when we decide to proceed, we factor out I of m comma n together by saying we have I of mn sine of n plus 1 of x cos n minus 1 of x. When you open up this bracket, I'll end up having n minus 1 of I of m comma n minus 2 minus n minus 1 of I of m comma n. Remember, plus times minus is minus. This is this and this is this. So you don't have to be confused of that. Then the next thing to do is collect like terms. But before I do that, okay, let me just do that once and for all. Let's bring this to this side. I'll end up having plus n minus 1 of im comma n. I'm only trying to collect like terms together. Then when this comes, I'll also have plus m of I of m comma n. So what I have left here is just sine of n plus 1 of x cos n minus 1 of x with the last, is the second term I have here. So I hope that is clear. And then in this case, I can easily factor out I of mn such that if this cancel this, I will have 1. Then if this cancel this, I will have n minus 1. Then if this cancel this, I will end up having just m. So trivially speaking, 1 will cancel minus 1. Agreed? Then I'll end up having sine of m plus 1 of x with everything I have here. Okay, n minus 1. So you're almost close to the final answer. So whatever I have left here is just n plus n. I end up having n plus n left with im comma n equals to this expression. Hence, we end up having okay. So yeah, in this case, to eliminate m plus n here, all you just need to do is to multiply both sides by its reciprocal. Um, multiply both sides by its inverse. So I'm multiplying both sides by 1 over n plus n. This cancels this. Hence, the final answer of I of m comma n remain as 1 over n plus n with sine of n plus 1 of x cos n minus 1 of x with this of I of m n minus 2. And this gives the final answer to what you're actually trying to look for. And then remember that this is equivalent to the question given to us. And this is an assumption. An assumption made for what? Integral of sine mx then cos nx dx. So that's very simple. So watch out for the next lesson plan, which is lesson plan H. So that is going to be based on exercise, and lesson plan I too will also be based on exercise. So then we round up reduction formula with that. So then the next thing after that is to move to the next topic, which is the Leibniz theorem. So I'll work on that anytime soon. Thank you.